It used to be fun to create things, right? What about today in the energy industry? What's it like to create today? Complex systems and processes abound, and the flood of data can make life difficult and confusing. Combining these systems and data streams effectively over the long term is often a major challenge. That's where Zenon comes in. The Zenon software platform makes it incredibly easy to run production and infrastructure systems. How exactly does Zenon work? With Zenon, you can capture all of your equipment data in detail and analyze it in real time. Zenon manages and maps systems and processes, helps you to compare data at a glance, and gives you full access to critical information about your equipment. Additionally, Zenon enables you to implement digitalization projects quickly, easily, and accurately. How is the software platform structured? Zenon provides you with a strong foundation of complementary features. The software is fully scalable and provides the optimal combination of security and flexibility. You can build your various applications flexibly on this software platform. Fully automate substations, manage energy distribution, and monitor renewable energy generation. So get started today and achieve your long-term operating goals with ease. Zenon, industrial software that makes your life easier.
Hello and welcome to our webinar today about effective operations and monitoring of distributed energy resources, in which we are going to discuss a few trends and practical applications in the industry. We'll be discussing the status of the energy industry, and we will have a look on how to set the stage for future-proof integration of especially large-scale DERs. And furthermore, we will be looking on and under the hood of professional renewable operations and monitoring software. My name is Stefan Hufnagel. In the recent years, I have been doing technical marketing for the energy industry at COPA-DATA. And today I'm with Louis Williams, who will bring a lot of practical experience and know-how into this session as an application and technology expert for energy systems automation. A little bit of housekeeping. The session, our presentations, will take round about 45 minutes, and after that we will have a 15 minutes Q&A session. So at any time, if you have any questions, if questions pop up in your heads, just feel free and type them into the Q&A panel. The session will be recorded, and after the webinar you will receive a follow-up email with all the information of the webinar and a link to the webinar recording. So at the beginning, let me talk a little bit about COPA-DATA. The person which you see here on the screen is Thomas Punzenberger, and is the CEO and founder of COPA-DATA. At about 1986, Thomas found himself in a situation as young engineer where automation was very, very hard, where automation solutions were very hard to generate or develop and establish. There were a lot of interfaces, a lot of proprietary systems which were not compatible with each other. And in order to establish and develop an automation solution, you had to do a lot of low-level coding. And at that time, Thomas had the idea to create something different, to make automation an easy task and develop and generate a system for that. And this was the inception of COPA-DATA, and it was the start of the development of the so-called Zenon software platform. Today, roughly 38 years later, COPA-DATA has grown into a globally acting company with more than 50 locations worldwide and a large network of partners and system integrators. There are well over 5,000 customers trusting in the Zenon software platform and more than 300,000 installations of the software system. COPA-DATA is not only active in the energy and infrastructure industry, but also in life sciences, pharmaceutical industries, in the food and beverage industry, in automotive manufacturing, and in various other automation industries. Now, in energy, the zenon software platform is used in several subsegments. For example, substation automation or network control systems for utilities. A number of renewable processes like hydropower or large-scale solar PV or large-scale battery energy storage. Industry electrification and microgrids is one of our segments, and the system is also used in infrastructure applications and public transport applications. So let me now dive a little bit into the current status of the industry as we perceive it. And I've written here the grid transition is in the full swing. That's what we see through the media. That's what we see through the requests from our customers. And that's what we see in various trends. So let's look a little bit into one of those trends, in this case from the International Energy Agency. And here we can see the investment behavior, the investment in power infrastructure from 2019 to 2023. And here on the left-hand side, in yellow, we see that renewables on a relatively high level is increasing. The investments in renewable infrastructure and renewable integration. At the same time, investments in fossil infrastructure are, let's say, stable or stagnating at a rather low or comparable low level. And at the same time, the investment into grids, meaning grid modernization, grid reinforcement, grid expansion, and energy storage also start to increase, which can be explained as a result of aging equipment, of aging infrastructure on the one hand side, but also the necessity to enforce and reinforce grids in order to being capable to absorbing or taking that energy flows from renewables, from volatile renewable energy sources. Nuclear energy, on the other hand side, starts to increase again on a rather low level. In some countries, at least, it seems that there is kind of a renaissance of this form of energy. Another trend, just to look at the composition also of the overall shares or of the overall investments, in this case from 2015 to 2023. And here we again see in this turquoise or light blue that renewable or investments into renewables are gradually or constantly increasing. Interesting is also that energy efficiency is quite a significant share and is also growing, or there are growing investments in this share, let's say in order to make better use of energy, in order to utilize energy and the diverse energy media better. Another significant part here is again the grids in general, so the investment in grid modernization, in making the grids more resilient, stable, and expanding grids in the background of a growing need or growing volume of energy which is required. And one additional thing I wanted to point out is that new applications like EV charging, electric vehicles, or battery storage are, since around about 2016-17, as they appear on the trend, continuously growing at a relatively small share, but in relative figures, it's quite a significant growth also in these sections. So who are the stakeholders? Who are the affected stakeholders which we look at in with our services and our product, but also in this webinar? It's first of all transmission and distribution utilities. So in the background of this dynamic environment, utilities are struggling with congestion. So the additional amount of energy and the volatile energy through renewable energy sources gets grids at certain areas into their limits. So congestion and guaranteeing or ensuring proper power quality is a major pain point for those companies. And we have renewable operators which appear in the landscape. So independent companies like independent power providers, they are often called, who own and operate certain larger scale renewable plants like large scale solar PV or large scale batteries, wind farms and things, or plants of that nature. And they somehow have to manage typically the connection to their local grids, to a distribution grid or to a transmission grid. They often have to manage diverse assets and distributed assets. So they have to somehow figure out how they manage their fleets. And in the end, of course, they wanna operate their plants as profitable as possible. And last but not least, it's industrial customers. Of course, their major concern and their major challenge is to stay productive and increase even productivity. But due to the experience of the energy crisis, of course, some of them also are going in the direction of self-sufficiency, getting more independent from external energy supplies and getting more self-sufficient. And of course, net zero is an important topic at this point of view. So these players or these companies are looking for potential after or behind electrification, electrifying certain processes, proper methods for energy management, increased and optimized use of energy, and of course hybrid operations. So on one hand side, I need to run my production process, my refinery, my manufacturing process properly, and on the other hand side, I want to coordinate, I want to orchestrate that with generation or storage from renewable energy sources. So the challenge is now, how do you effectively innovate in this landscape where there's a critical infrastructure, so something that has to be up and running 24/7. It's an environment with quite complex regulation, and there's like new technology needs to be utilized in order to make certain solutions even possible. There's a high interdependency, for example, really on physical level, right? There's an exchange of energy, there's an exchange of materials, which has to be continuously flowing, and on the other hand side, also on an informational level. Systems are being interconnected, OT systems, IT systems, so there's a high degree of interconnection and interdependency. And last but not least, there's always legacy. So think of utilities who have to operate substations, who have to manage substations, which have been built decades ago and have been automated with systems which are ages old. On the other hand side, as a manufacturing company, you will also have some older machines, some older equipment in your shop floor, and anyways, there will be systems from different vendors all around. And here, the zenon software platform comes into play, which solves quite a big share of those problems. So let's have a look what the zenon software platform actually is. With the zenon software platform, you can connect to any device and equipment, to any asset. That comes due to the fact that the zenon software platform has a very, very big library of communication protocols, far more than 300 communication protocols, which are ready to use in order to connect devices from different vendors and from different assets. As soon as you have the information and the data in your system, in your solution, you can manage the data, you can structure the data, you can archive the data, you can forward or recalculate the data, you can forward the data to other, let's say, third-party applications. Visualization and situational awareness and control are very, very important parts of the zenon software platform as well. Think about processes for substation automation. If you need to control critical equipment, circuit breakers, disconnectors, transformers, and things of that nature. Furthermore, you can do with data, on the one hand, archive data, but also live and real-time data, do advanced analytics and reporting in order to improve the efficiency of your assets or of your operation, building KPIs, analyzing trends, for instance, in order to operate or in order to optimize the efficiency of your processes. And think about what I've said before, the founding idea of the whole technology of the zenon software platform. Engineering is pretty easy. It is all standardized, and this is mostly based on templates, on ready-to-use building blocks, which can be assembled together in order to form a solution. And there is, in the first approach, in the first instance, no coding or no programming skills are necessary with the zenon software platform. So in the end, here is an overview. It is essentially building the zenon software platform is building a robust and secure interconnection layer, integrating all the assets you have in diverse plants, in substations, solar PV, wind power, and so on, and making it possible to, for example, do local visualization, local control, but also doing remote and central visualization and operations management. And due to the fact that the system is equipped with a lot of connection possibilities and connectivity possibilities, it's always also very flexible to integrate auxiliary systems. Like, think about a large-scale battery, which typically needs some kind of HVAC system in order to control the temperatures in the process or in the environment, or an additional fire detection system, for example, a building management system, which requires certain communication protocols in order to be monitored or controlled. Luis will later give you an overview on the specific possibilities of the system here. Now, in order to make it a little bit more tangible, how zenon looks like in the real world, I'm bringing two recent case studies with me. The first one is in Korea, a solution which is installed in Korea at Daenyang. That's kind of an independent power provider, as I've mentioned before. And as you can see here in this illustration, in this picture, which I've taken from their website recently, in the last 20 years, so since the founding of that company, they have built specific sites, specific plants, like large-scale battery storage, large-scale solar PV, or wind farms. So as you see, scattered across the entire region of South Korea, they have these plants. But during the establishment of these sites, there was no real focus on standardization. So they ended up at a certain point with single installations, single wind farms, which were all equipped with an OEM solution, an OEM software for local operation. So they did not really have like an overview or a central visibility of their portfolio. And this is what they recognized over time, and this is where zenon came into play. So in the end, in the recent months, within 12 months, they have been able to integrate 9 plants out of their fleet up to now, plus substation, into a central operations and monitoring application. And as you can see here at the bottom left, this enables them, for example, to having a real-time dashboard overview where they have the production figures, where they have the states, alarm situations, and certain KPIs on the screen at the central control room. At the same time, they can have central alarming, central event logging, and they can do central reporting about production figures of their sites. On the other hand side, you can see at any time they can drill down in the specifics, in the details of the single plant. So they can have, for example, a look into the statuses of the turbines, into the states of the assets. So that's a tremendous benefit, obviously, having that at a central place at any time, rather than going to the single locations and having to instruct people to deliver the information you need, or to issue commands which you want to expose to the specific plants. Second example is a system which runs in Germany at the Potsdam Chamber of Crafts. This is a training and test center for modern energy technology. And as you can see in the picture and in the schematic diagram, it is a composition of a lot of different assets. For example, there's 11 independent photovoltaic plants, there's wind power generation, there's a charging station, home storage system, and a larger scale battery energy storage system. And in the end, they used zenon in order to combine all that into a central hybrid microgrid energy management system. Let's have a look on the detailed screens. So now you have the possibility to observe the entire system in real time. Like on the bottom left, you have power curves. You have an overview on the actual generation and consumption of the diverse assets. In the middle, we can see the circuitry. This is a very important aspect of any energy application, to see what is happening on power switches, circuit breakers. What is the status of lines? What is the status of transformer or grid connection, which Luis will later talk in more detail. Then we have, for example, a Sankey diagram, which shows us the power flow. So where's the energy generated, or which amounts of energy are generated on the one hand side, and on the other hand side, where is this energy consumed? Where does it go into? And again, the key quality of the zenon software platform here is, next to visualization, is the ability to connect to all these diverse assets. Some of the protocols which are used in that application are shown here, like VHP Ready, 6870, 61850, or Modbus. There could be also something like OPC-UA OPC-UA in the system, or DMP3, or whatever protocol you can imagine. So this brings me to the end of my part here in the webinar, to introduce and giving you an idea what we are doing and what the zenon software platform is doing in the current energy environment. And now I'm handing over to Luis, as promised, who will take us into some of the details and giving us information about some of the fundamental concepts of DER automation. Luis, the stage is yours.
Thank you, Stefan, and thank you for the introduction. So my name is Lewis Williams, and I'm very happy to be in this webinar today to give you some insights into DERs and also how Zenon can be used in the DER sector. My opening slide, a lot of buzzwords. The topic of DERs is extremely wide. Not only do we need to focus on each specific type of DER, you can see some buzzwords here from various battery energy storage, wind parks, solar farms. But first we need to understand why we deploy DERs like we do. So I've picked out a few examples of potential use cases and requirements for a DER deployment, for example. So let's start off with quite an easy one to understand. We have a specific facility, and we want to ensure that we have emergency standby power or backup generation. And some of the considerations that we first need to think about is, how reliable is our supply or our service? Are there a high amount of service interruptions from natural disasters, or just from the quality of the service itself, depending on where we are geographically in the world? Then, always a good consideration to do is we need to identify our critical loads. So it could be for critical infrastructure, a hospital. Certain devices obviously need to be have standby power in the event of an error. Then also what we need to identify is the generation requirements for our emergency or standby power. How long is my service going to be unavailable for? Maybe the DSO utility has long service restoration times, things like this. So these are considerations we need to look into. What can we deploy? One of the cheapest and most often used ones is still diesel or gas generators. They are highly mobile, very cheap, and this is still a very good solution, especially for emergency or backup power, distributed energy resource. The same with micro turbines, slightly more expensive, a more of a permanent solution, but again viable. And if we look into the renewables, then battery energy storage systems. Now, as one consideration, we can go into a lot of detail on what would be the best technology, battery energy storage-wise, to deploy. There are a lot of benefits to lithium-ion batteries. Zinc bromide batteries have more of a medium duration, but are slower to respond. This is what we need to consider when we look at battery technologies. And of course, we can make our emergency standby backup power generation even more flexible if we combine our storage with a hybrid system, for example, generation and storage. Another use case, standalone or microgrid systems, where our behind-the-meter DER must meet all of our load requirements for the facility or the load which we require to have a service for. So typically, sometimes they are located far away from a traditional utility, either geographically or the utility cannot offer a specific service. We need to consider again how our service requirements look like. Is it a requirement that it's a 24-hour, 7-day-a-week supply, or it could just be throughout the certain times of the day or night? Also, the geographical considerations, the availability, as Stefan mentioned before, of various resources. Should I choose a diesel or gas generator? Do I have the resources available to me at my location? Also, the environment limitations. We might have a facility. Do I have the landscape to potentially deploy a renewable generation DER, such as solar or wind? Also, the climate. Sounds quite simple, but does the wind blow regularly in the area where I am? Or do I have high levels of solar radiation penetration in my location? With these considerations, then we can finally start to look into possible DER technologies for our area and for our requirements. Okay. And then last but not least in these examples, so a demand side management. Let's take peak shaving. I want to reduce my outgoing costs for my electricity supply. So the first stage is obviously to identify where my peaks are. The second stage would then be to identify the peak duration. So does my peak demand last for 5 minutes? Does it last for an hour? Is it a longer duration than this? And then finally, how frequent are my peak demand? Do they occur multiple times a day? Do they occur at a certain time each week? Do they occur on a weekend? How often do they occur? So when we deploy DERs to counteract our peak shaving, then we can start to make some more considerations. For example, if we went down the road of deploying a battery energy storage system, potentially lithium-ion battery storage system technology, because it's typically has a fast response time, then what we can also start to consider is where are my low demand points for my facility. Do I have a chance then to recharge my battery to then be alleviate my peak demands in the future? So to even flatten my supply curve even more, leading to a more secure supply. But also, let's identify our attributing peak loads. What is causing my peak loads in this scenario? Here we have an example where my peak loads could be happening or occurring at midday for whatever reason, whatever my loads might be. So this would mirror perfectly the generation profile, for example, of a solar PV. If my main loads are air conditioning units, which typically run during the day for the heat. So these are just some considerations which we can look into as to, one, our DER use cases, and two, which technologies are the best fit for our requirements. So Stefan mentioned that Zenon allows us to connect with a lot of different devices, different DERs. Here we can see an information exchange for DERs. So in the middle on the bottom, we have deployed various types of DERs. We have a solar PV, battery energy storage, a diesel generator, and a wind farm, each potentially with their own out-of-the-box HMI, local HMI, and a local controller. What we can do with Zenon, and a lot of restrictions can be seen with these local offerings. It could be an embedded offering from the manufacturer in the inverter, is that they are not very flexible when it comes to comparing different DERs for the likes of performance comparisons. They don't really offer robust reporting techniques and very limited control possibilities. So what we could do is aggregate or combine these into a DER SCADA monitoring and control system, where we can then create reports and analytics comparing each of the DERs and also some forecasting, calculate real-time KPIs, and have this in one platform as a system. On the right would also be a use case for a DER aggregator, which could provide data about the DER to a virtual power plant, for example. So a virtual power plant, regardless of where the DERs are geographically located, thanks to the DER aggregator, can consolidate multiple DERs in one system and then react based off of market needs and also the situation or the status of each of the DERs. At the lower level, at the bottom here, we can see a physical connection potentially to a distribution grid via a PPC, a point of common coupling. Here is also found protection for the specific DERs. And again, at the distribution substation or grid connection substation, we would have a substation HMI to calculate the load flows, to safely switch the circuit breakers, to monitor the disconnectors and the transformers, things of this nature. So if we look at this topology, how can we retrieve data from all of these devices in this quite elaborate information exchange? As you've seen just pop up on the screen, one of the helpers, let's say, in this sector, specifically for solar PV, is a standard called SunSpec. Now, SunSpec base data models on Modbus TCP, and it's extremely widely used and embedded into inverters from most of the big names in manufacturing, and also for weather systems, smart loggers, things of this nature. So SunSpec would be a great help here, but also in battery energy storage, where they do something similar for the battery bank, the battery racks, the strings. So we can also integrate data models for the various aspects of a predominantly lithium-ion battery-based BESS technology. When it comes to diesel generators or gas generators, for that matter, a wide array of protocols are normally supported, but more often than not, you will also find classic protocols such as Modbus RTU or TCP-based Modbus. When it comes to wind farms, here we see OPC, IEC 61400 data models, and again, Modbus. So all of these can be connected to with Zenon, the data retrieved, and also set points sent down from the DER system to control the DERs as required. But as soon as we start to get into the realms of grid connection, one of the bread and butter for Zenon for many years has been substation automation. And here we start to see the likes of 61850, DMP3, 6870 in our grid-connected substations. And if the DSO implements a distributed energy resource management system, or DERMS, then our DER system could also pass on the relevant data to a DERMS platform. And here we start to see almost a sister protocol to Sunspec, DMP3 MESA or MESA. And what they do is they model standard data models for the exchange between the DSO and the DER system and the DERMS, so that this is all standardized regardless of the amount of DERs that they are communicating to. And also the likes of 6870, 104 can be found here as well. So when it comes to connectivity, here we have some typical protocols which Zenon supports when it comes to communication with DERs. As mentioned before, 61400 for wind power, MESA DER standards based on DMP3, Sunspec Modbus based, something we haven't touched upon, but it will be a focus in many years when it comes to technology, and especially with the onboarding of vehicle to grid technology, is the Open Charge Point protocol for electric vehicles. And mostly found in wind in the energy market, but widely used elsewhere, is the OPC UA server and client. So not only do we have the possibility to acquire data, but also to forward it to the relevant parties which wish to communicate with OPC UA. When it comes to the grid connection, then here we have our IEC 61850 MMS client, but also an MMS server, also supporting Goose. So it's a webinar about DERs, but extremely beneficial to have a Goose publisher subscriber for various use cases within the substation HMI as well. And various other protocols which are typically found in the substation automation sector. I think Stefan mentioned it before. If we take battery energy storage systems as an example, then the added benefit of supporting standard and proprietary protocols could be that in the likes of lithium-ion battery technology, it's extremely important to keep the temperature of the batteries and monitor it. And this is typically done by a heating, ventilation, air conditioning system, or HVACs. And these typically communicate via a BACnet protocol, some cases KNX. So we're starting to veer into the almost smart building protocols here. But these are extremely beneficial then to add an extra layer of visibility when communicating with such of these DERs. And let's not forget the ability to monitor production, exported, generated energy requires metering or an energy meter of some sort. And here we can specifically focus on the majority DLMS or COSEM IEC 62056 to communicate with our meters. So let's take a look at our energy landscape within Zenon, and let's focus on the top right, where we have our grid scale or utility scale DERs, where we can see wind power on and offshore, depending on the size. Obviously, of the wind power, it might be a requirement for high voltage DC or offshore stations. And then some of the other DERs, which we've touched upon, battery energy storage and solar PV. Before we just take a look at some of the demos in Zenon, just let's think about some of the O&M considerations when it comes to DERs. So Of course, they need a monitoring and supervisory solution in order to control the DER. It needs to be able to aggregate and standardize data, categorize data into specific alarms, forward data, things of this nature, and also archive data. And once we've archived data, then we can use it to calculate specific KPIs. So based on historical data, what are my KPIs for the specific DER that I've chosen to deploy? Contractual frameworks, obviously they're under a specific contractual framework when it comes to guaranteeing that a DER maintains a certain level of efficiency. This could be a hard limit when it comes to solar PV or batteries. They also need to obviously have a contractual framework which declares the length of the O&M contract when it comes to that specific DER. Something we'll touch upon in a few slides is also grid connection compliance. What do we need to consider when we are connecting a DER to the grid? And last but not least, preventative maintenance. What does my historical data tell me, and also my real-time data tell me about the state of each of my components? So then I can plan accordingly and maintain my assets. So a lot of information, and Zenon can do a lot of things, supports very many protocols, which is why we wanted to in the last couple of years give it a specific focus when it comes to specific application requirements. So in the background here you can see an example of a solar PV generation demo or application example with Zenon. All of these applications are object-based. So what that means is typically in a solar PV, we are talking about multiple instances of the same asset with which we need to connect to. So be it a smart logger or a data logger, inverters. And this is also similar for other DERs, typically wind turbines, things of this nature. They're all the same. So if you can create an object or a model which fulfills these requirements and instance them multiple times, this is what these demos are based off of. So here is a short overview of what the Zenon software platform contains in a solar PV context, and with which protocols we typically retrieve data from and also forward to the relevant stakeholders or utilities, things like this. And the same goes for battery energy storage systems. As I mentioned before, SunSpec also allows us or has defined various data models to interact with aspects of a BESS system. And in the demo behind me, this is what we can see here. So various parts of the BESS include the banks, also the racks, all the way down to module level, depending on the size of the installation itself. And again here, so as I mentioned before, connection possibilities to BESS specific components, so i.e. the battery management system or BMS, conversion systems, also fire suppression systems, and last but not least, our HVAC systems. We spoke a lot about KPI calculation and things like this, extremely beneficial not only to stakeholders who, for reasons of profitability and things of this nature, obviously need KPI reports, as well as the operations and monitoring guys. So when it comes to reporting in Zenon, we have reporting solutions which allow you to customize KPI report calculations based off of historical data, automated delivery of such reports. So we could create multiple reports for the O&Ms So that might be focused on more maintenance and efficiency of various devices within the DER, or the deterioration of various devices in a BESS, for example. Whereas for relevant stakeholders, they also receive other reports, and these are delivered automated delivery and created automatically as well by our reporting solutions. One of the standards involved in this is 61724 IEC. And here, especially in the top right, these reports are defined based on the criteria which this standard defines. So specifically for solar PV, such calculations for performance ratios, various system losses within the system itself, and also capture losses for the solar PV panels. So a few considerations when we want to connect a DER to the grid. Here is by no means not a comprehensive list, but there's a few standards in here which are quite relevant, especially IEEE 1547 and the 2018 basically provides the groundwork for how a DER should react under abnormal grid conditions. So abnormal grid conditions, basically in a nutshell, means abnormal voltage levels or abnormal frequency. So how a DER can actually help in stabilizing the grid, and in an extremely abnormal condition or critical condition, how it should react if it needs to disconnect from the grid, and also how it should behave upon reconnection when the grid conditions are normalized. So here we can see on the graph just a small example of one of the guidelines or rules defined in such standards, low voltage ride-through, how DER should react in this scenario. But what I also wanted to point out in this is you can see the different colored lines in this graph, and each of these represent a different country. So the geographical placement of where we connect the DER to the grid is country-based, but also within the country, defined by the utility or the DSO. Whoever you are connecting with will have their own specific set of standards and guidelines which we must adhere to. And when it comes to grid connection, again here the important aspects of a substation HMI automation solution, safe switching of various switch gears, so circuit breakers, disconnectors. In the background here you can see a topology modeled in Zenon, and also not just nice colors, but also the added possibility to add a voltage regulation, but also load flow, in order to better get an idea of how the grid is looking like and how my DERs connected to this grid are behaving in certain situations. So if we look at Zenon and the challenge of DER deployment as a whole, one of the major USPs of Zenon is the ability to connect with a lot of different DER technologies and standards and ways of working, also bolstered by the suite of features which we have in the classic substation automation sense. So the larger the DERs, the more often or not, then we can consolidate not only the control and monitoring of the DER itself, with then the substation grid connection. And that wraps it up for me. I will welcome back my colleague Stefan, and I think we can start the Q&A session.
Thanks, Luis. Thanks for these detailed explanations and insights. And now for the Q&A session, we'll welcome another colleague of ours who joins us from Stockholm, Jürgen Resch, who is the director of the energy industry team here at COPA-DATA. Welcome, Jürgen.
Hello, everybody. This is the Nordic outpost of COPA-DATA speaking. I was monitoring the questions in the Q&A area throughout the presentation, and they were quite interesting questions, I have to say. Most of them, or some of them, I could even answer. So let's start with the first one. Let's start with this. What advantages does zenon offer over systems already being used for monitoring systems operating in the utility scale PV and battery energy storage?
So maybe I'll answer to that one. From my point of view, of course, it always depends, but a lot of systems which we see and where zenon comes into play at, let's say, central operations and monitoring applications is that they are really tailor-made and perfect for the system and the process and the assets they control. But it is then potentially difficult for an end customer to access data and doing more with data, or let's say to having assets for different processes, let's say a solar PV, the inverters in a solar PV plant, and next to it having like wind turbines, where there are a lot of different OEM solutions out there, and then being able to interconnect them. And here zenon comes perfectly into place because we can adapt to the different interfaces, and very often systems, OEM systems, have an own or have their own proprietary data models, and with zenon you can adapt to that and build kind of an intermediate integration layer and bring, as in the example in the case study I've mentioned before, I've explained before, bring all that into a central place and you know add some functionality and yeah, create some benefit out of that.
Yeah.
Okay.
Just to add to what Stefan just mentioned, as soon as you come into a situation which is slightly out of the norm, let's say, or you have multiple DERs, then this is when zenon comes into play. As soon as you step out of the scope of what an OEM offering for a substation specifically focuses on, then either you have 10 different applications for 10 different DERs, or you can consolidate this into one platform.
Mm-hmm. Then I have another question, a little bit related to the first one. Can you connect to inverters from popular manufacturers?
Yeah, so I think I discussed this slightly or covered this slightly in the presentation. So we have added the SunSpec data models into zenon, which allows you to connect simply by adding an IP address to inverters from, let's say, the big players, the Huawei's, the ABBs, the Siemens, whoever it might be. And SunSpec is quite a big standard, actually. And you can find it on their website, who actually has implemented and is compliant to SunSpec data models. And I would say the vast majority of the big brand names are already SunSpec compliant. So, and even if they're not, then obviously, you know, depending on the device you want to connect to, there is a handbook which basically tells you the data model of this proprietary device. And it will obviously give you information regarding which protocol the device supports. So even if it isn't SunSpec compliant, then you will be able to connect to it and retrieve data in one way or another with zenon connectivity options.
Okay. And then we have a bunch of questions about the topic around microgrids. So the question is, first, has zenon been used for microgrid applications? I think, Stefan, you can answer that question. And the second question is about how do we deal with logics that is needed to run a microgrid application to manage the microgrid.
Yeah, so as you've mentioned, one of my case studies, for example, was kind of a microgrid application. That was the Potsdam application with the diverse assets. And we see a lot, although we don't see all the applications which are done by our system integrators, we see a lot like in the area of university campuses, in the area of mining application and applications of that nature. In the end, I think we have to be a little bit careful with the term microgrid. Maybe for me, I always tend to say there are two sides of a microgrid application. On one hand side, it's like the protection side. So there could be protection equipment from protection OEMs, which builds up and manages a certain microgrid, and these devices typically also bring a certain functionality and algorithms in order to manage certain things in the microgrid, especially the protection functions, the proper isolation and things like that. So this is like the protection side of a microgrid. And in this case, Zenon is a perfect complementary hooking up to these devices, making processes visible, and also Zenon brings certain security functions, protection functions with it. So it's a matter of the specific application, how you set that up so that the systems work complementary here. And on the other hand side, a microgrid could be, or microgrid control could be about things which Luis mentioned before, like doing demand side management, regulating generation, doing peak shaving, and things like that. And there are certain functions in Zenon, also used in the case study, which I've mentioned. However, these are also always very specific to the use case, to the application, and probably it's necessary to having an advanced algorithm implemented and integrated into Zenon, which is also possible. The system is very open, and you can always integrate specific control means, for example, by means of using software.
Okay, Luis, anything that you want to add here?
Yeah, so I was about to add on a technical level where these control algorithms would be hosted, and probably something we didn't dive into, let's say, during the presentations, is as Stefan just mentioned, the 61131-3 soft PLC environment, which is bolted on to in the Zenon platform, and here we have many experiences with integrators deploying this behind the SCADA server or integrated within the SCADA server to provide such control algorithms. So in there are PID controllers. It's a soft PLC environment like any other, and this would be the perfect, let's say, environment in which to host a controller. I think when it comes to microgrids, obviously a controller which focuses on its own part, so a controller which purely focuses on the solar PV battery and load with an orchestration control algorithm on top, and this would be then the microgrid controller, let's say, would be a potential approach for a microgrid control algorithm. Yeah.
Okay, great, thank you. And then there was a participant who is actually running his substation SCADA of a wind farm based on Zenon already. And now the wind farm itself will be hybrided with a solar PV farm. And the question is if the Zenon substation system can be expanded to this hybrid plant.
Yeah, I think I'll take this one. So when it comes to extension or expansion of already deployed Zenon installations, let's say, on the technical level, you have an area where you engineer and an area and a system which actually runs the application on the server. And an extension of possibly a protocol extension. So they might need additional drivers in order to communicate with the new devices. potentially some added functionality from various zenon modules is required. And this is simply a matter of a license update. There's no reworking of the project. You can simply add the necessary drivers, retrieve information, however many new screens you need to represent this extended data, and away you go.
Okay, thank you very much. It's 5 o'clock, our time zone. Stefan, you are the host.
Time for maybe one or two additional questions.
One or two more questions. Okay, let's go. We are coming now from wind to goose, because you mentioned it in the communication. So the question is, what are the main benefits if we use goose in the HMI?
I think to discuss that, it's necessary to mention where this goose actually happens. So as Luis mentioned before, we have this soft PLC engine, this 61131 environment, and this one has an integrated IEC61850 MMS, an IEC61850 server and goose driver. So it can act as a goose server and as a goose subscriber. So you have this soft PLC engine, which you can deploy everywhere on a regular PC, on a server, or even on an embedded device. This means that you can somehow tie into the goose communication. For HMI, it means, for example, you could like receive goose messages and for example do alarming based on that, for like observing the goose communication, doing goose observation and detecting if there are any gaps in the goose communication, for instance. In another use case, you could use this, for example, to do substitution of a goose device in a situation where you need to switch off, deactivate, or do something special with an existing device. So these are some ideas how you could use that technology on the HMI level. But this is maybe, if there are specific requirements, contact us. We can go into the details and discuss your specific use cases. I think that's the best.
I think also that this answer cannot be done within a few lines or a few seconds. This needs to be discussed on a longer range.
Yeah.
Stefan, last question.
One question, yeah.
One question. Actually, it has nothing to do with the content, but I need to state it because it was so funny. Somebody was asking if you, Luis, have an Austrian Liverpoolian hybrid accent. So where do you come from, actually?
Yeah, that's quite correct. What you've just said. So yes.
Okay,
I need to
leave it with that.
On one of those, I think.
Okay, thank you very much. Stefan, I hand over to you.
Thank you very much, Jürgen. Thanks for the moderation of this Q&A session. I think that was a call to act to contact us if you have any special use case and solution to discuss. So thank you very much for your attendance. I hope we could give you some inspiration for your upcoming projects. Stay tuned for our upcoming webinars and other events from COPA-DATA. Thank you very much. Thanks, Luis.
Thank you.
It was a pleasure. See you next time. Bye-bye.
Bye-bye.